Okay, Algebra 2 students, we're going to be reviewing for Unit 1 and Unit 2 both together today. Doing them both together because some of the material is similar and there's not a whole lot of material in these two units, which looking back at it now, it seems kind of silly because we did struggle with Unit 1 and 2, but there's just not a whole lot in there, and we've seen some of these topics so many times this year, it's almost laughable. Anyway, what we did is we started off in Unit 1 with a very lengthy discussion about domain and range, which is a topic that is not new to us. We saw it back in Algebra 1, and we've seen it a ton this year. Okay, and of course the domain is all the possible x values for a particular graph, and the range is all of the possible y values that a particular graph has to offer. Okay, now keep in mind that domain does not mean where does the graph cross the x-axis. Okay, that's called a solution, and range does not mean where does the graph cross the y-axis. That's a y-intercept. Okay, so if a graph exists anywhere in the Cartesian coordinate plane, then there must be values in the domain there. There must be values in the range there. Okay, so let's make sure we get these definitions straight. Now in a graph, when you're reading the graph, if you run into an open dot in the graph, an open dot means that that is a boundary. It is a location of the graph, but it's not actually in the graph. A closed dot would also be a boundary, but it is actually included as part of the graph. So when it comes time to write down things like domain and range, we use what we call interval notation mostly, and you will use parentheses to represent open dots and brackets to represent closed dots. So parentheses are information that are not actually in the graph, they're just a boundary, and brackets are information that is actually in the graph. If infinity ever becomes part of the interval for domain and range, which we've seen about 1,000 different instances where infinity is needed, okay, infinity always gets parentheses, and specifically the reason for that is because you cannot go to the number line and point at infinity. You cannot put a dot on it, okay, because it's by definition it is undefined. Okay, so we looked at several examples, okay, of domain and range, and obviously you can see the answers on there, but just real quick, the domain exists in this graph from -3 to 0, meaning the graph is everywhere in between the value -3 on the x-axis and the value 0 on the x-axis. -3 gets a bracket because of the closed dot. That means that endpoint is actually included as part of the domain, and 0 gets the parentheses because of the open dot. So 0 marks where that graph ends as far as the x-axis is concerned, but it is not included. And the similar explanation for the range. You're going to begin at 0, and it is included, and go to 4, and if 4 is not included. Now with domain and range, something we've struggled with all year long. Okay, just a little bitty technical detail here. Domain and range are always least to greatest. So always from -infinity to +infinity, and then you list off the values in the intervals as you come across them, moving from least to greatest. Okay, so in this particular graph, same basic idea as far as the starting point, but the opposite end of the graph heads off to infinity. So in this particular case, our domain is going to begin at -3. We get parentheses on -3 because of the open dot, and then the graph never lets up. It continues on infinitely because of the arrow on the other end of the line. So our domain is going to be from -3 not included, to infinity, and infinity always gets parentheses. From the range coming up the y-axis, we first run into a value at -1, but it is not included, and then the graph never ceases to stop rising, so it goes all the way to positive infinity. Okay, again, domain beginning at -3 included because of the closed dot, continuing on to +5, 5 not included because of the open dot, and the range coming upward begins at -2 included and ends at +3 not included. If we run into situations where we just have little bits and pieces of data, not an interval, meaning the domain begins here and ends there, but it's just kind of little blips in the graph, then we use the little curly braces, the set notation, to list off those values. So in this case, we have domain values existing at -4 and at 0 and at 3, but the curly braces indicate to us that it is just those values and nowhere in between. In the range, we have values at -3 and +1. Now, please note that in the range, there are 2 points that are have the -3 value, but when it comes to this set notation, it is not necessary. In fact, it is considered to be incorrect format to write the same value more than once. So in this case, we have 3 values in the domain, but only 2 in the range. That would indicate to us that at least one of the values in the range has been used twice. Okay, we also got into the vocabulary of functions and functional notation in Unit 1. A function is simply a graphable expression where each value of x has one and only one value for y. Okay, we spent a great deal of time this year talking about functions and their properties. Okay, but anyway, we kind of just started exploring the very basics, taking an equation, and when any x value, if we took any value from the domain and plugged it into the equation, no matter what the x value was, we only got back one value for y. That is a property of a function. If ever you were able to plug in a single x value and get back more than one y value, and we've seen those here recently with the conic sections, okay, if ever that happened, then we would not have a function, like many of our conic sections have not been functions. Okay, we've also seen sporadic appearances of what they call a mapping. A mapping is basically a graphical representation of how your domain and your range are related to each other. Typically what you have is you have a oval or circular type set drawn, and individual values within that set are listed out separately. Okay, and typically what you have is you have a set for your domain, like the x's there on the left, and a set for your range, like the y's there on the right, and then arrows are used to track from one set to the other set which values belong to which corresponding values. Okay, this is a very easy way to identify whether you have a function or not, because if any domain value connects to more than one range value, well, we've got one x that has more than one y. That would make it not a function. Okay, so we looked at some examples of that, and we can see in the cases at the top, those are good functions. It is definitely acceptable for each x to have just one y, like the top left. On the top right, we see that 2 different domain values have the same y. Well, that puts 2 points basically side by side, left to right, and that's okay. But in the bottom left, we see we have one x value connecting to 2 values from the range. Okay, so one x has more than one y. That's going to stack 2 points on top of each other vertically. That's a no-no when it comes down to functions. And of course, the one there on the right, that one x value has 3 different points stacked vertically. That's definitely not going to work. Okay, another thing that we talked about is if you have an accurate graph, and what we typically mean by an accurate graph is one that you probably did not draw yourself. Okay, if you have an accurate graph, we can always use what we call the vertical line test. Okay, but any location in the graph, you can draw a vertical line down through the graph. And if you place infinite numbers of vertical lines down through the graphs, if none of the vertical lines actually hit your graph more than once, then you have a function. But in the cases like the one in the top middle or in the bottom middle, you can see that there are at least one location where you can draw a vertical line coming down through the graph, and it will make contact with the graph more than once. That means you have a single x value that is trying to have more than one y value, and that is not a function. Okay, once we have decided that we do have a function, then we typically see what we call functional notation. And in functional notation, typically the value of y has been replaced with the symbolic representation f of x. Okay, so when you see f of x or g of x or h of x or any other of those notations, that simply means that the problem has already been determined to be a function. Okay, so that was the end of the first lesson. The second part of Unit 1, we came back and we looked at the idea of dependent and independent and discrete and continuous. Now, a little bit of vocabulary here. Over the years, we've collected a lot of different vocabulary about what can you call X values. Okay, well, we've called them X values. We've called them domain. They are independent variables. And the same thing with range, Y values, also called range, also called dependent variables, and so on. Okay, and anyway, we kind of talked about the idea of a functional equation kind of being like a machine. We input values into our function, and our function basically delivers us back values coming out of it. And since we have the definition for a function and we know what it is, we kind of know what kind of values to expect. Okay, but a couple of extra vocabulary terms in there. And back from your days in geometry with transformations, when a value has not been altered, that's what we call a pre-image. After it has been operated on by some type of a transformation or a function, then it becomes an image. So typically, values in your domain can be referred to as a pre-image, and values in your range coming out because of those X values are what we call our image. Okay, and same thing with this idea of the function machine. You also may see it termed input and output for domain and range. Okay. We also talked about the difference between discrete and continuous. Some of you are still grappling with this. The word continuous in algebra does not mean what it means in the English language. Continuous does not mean it goes on forever. Continuous simply means there are no breaks or irregularities in the graph. Okay, so like the graph on the left-hand side, it is not continuous because of the break that exists at the y-axis. That was what we would call a discrete graph. The one in the middle is continuous, not because it goes on forever, but because in the domain that the graph exists in, there are no breaks or irregularities to it. Okay, the one on the right side would be considered to be discrete because there are breaks or gaps, and it's not to say that every graph that you ever see is going to be discrete if it has points in it or plots in it like this one does. Okay, it is possible that it might still be continuous with just plots and points. Okay, the point is that it can't be just random. Okay, so like this one, there's 2 steps in between the left point and the next left point, and then 3 steps in between the 2 middle ones, and then 3 steps. It's not a consistent step size from point to point to point, so we have to assume that there is information or data missing from the graph, and that is what makes it discrete. So don't think that continuous means lines and discrete means points, because that's certainly not the case. We are looking for breaks or irregularities in the graph to decide if we are continuous or discrete. Okay, so I gave you several examples on there, so let's run through those real quick. Okay, the interval from negative infinity to -4 and -4 included is continuous because on that interval, including the point -4, there are no breaks or missing pieces of information from the graph. From -4 included to 0 not included, we would have to say that that interval is discrete because of that open dot at -3 in the domain. The interval from -3 not included to +2 not included would be continuous because in between those 2 points we have, even though it's a goofy little wavy line, there's nothing missing from it. And since the interval did not ask us to include the endpoints, then that is definitely continuous. And that's kind of the way these guys are read. Okay, that is basically it. That was all of the information that was in Unit 1. Okay, so looking back at it, hopefully you're kind of wondering, how on earth did I ever miss that stuff when we did the Unit 1 test? Okay, but there's that, and now we'll have a look at Unit 2. Okay, Unit 2 is where we kind of went face first into the whole parent function idea, and then that ended up being nearly a year-long discussion looking at the parent functions themselves. Okay, so right off the bat, okay, a definition for parent function is the most standard unaltered form of an equation or a graph. That is known as its parent function. Now, we've seen a lot of brand new functions this year, so we've kind of started off several units looking at the parent function and then going from there. Okay, so the first one we took a basic look at here back in Unit 2 was the basic quadratic. Now, most of us were familiar with the quadratic equation somewhat and what it graphs, which is, of course, a parabola. We were familiar with it somewhat from our travels through the last couple of units in Algebra 1. Okay, but the basics of a parabola is, of course, its parent function is f of x equals x squared. So our basic parent function is a parabola moving upward, and its reference point, its anchor point, if you will, or as we've learned it here in recent months, its vertex is positioned at the origin. Okay, we also looked at the cubic function, and we did spend a little time talking about the cubic function, but haven't used it a whole lot. And the cubic function is the result of when you have one variable in the first dimension and the other variable in the third dimension. Now, the basic parent function for the cubic is f of x equals x squared. Okay, so here is your basic cubic function. Okay, obviously it comes up through quadrant 3, bends through the origin, passing through the origin into quadrant 1, and then bends again heading upward. And if you haven't figured it out by now, you can always predict how many bends a graph is going to have by looking at the degree of the exponent, the degree of the equation, the highest exponent. The number of bends will always be one smaller than the highest exponent. So in this case, we have x cubed, so it will bend one smaller than 3 would be 2. It's going to bend twice, just like your parabola a screen ago had x squared. Okay, one smaller than the 2 for that exponent would be 1. Parabola only bends one time. Okay, so it opens upward as it travels from left to right. It passes through the origin. That's your basic cubic. We also spent a good bit of time in the spring semester looking at the exponential function. Okay, this one's a little bit more complicated, but we did get the basics of it here. Obviously, the exponential function travels along the x-axis in quadrant 2. This one is anchored at the positive 1 on the y-axis, and as it crosses over into quadrant 1, it was more horizontal, but as it crosses into quadrant 1, it becomes more vertical than horizontal and heads off toward infinity. Okay, square root function. This one's kind of a little bit of an anomaly. It doesn't seem to match up with any of the other ones. Okay, but the square root function is the function of the form f of x equals the square root of x. Now, dealing with the square root of x, we should know by now that the basics of that equation, it's impossible to get negative values to come out of a radical. So our graph is going to exist entirely in quadrant 1. It kind of launches from the origin. The origin is its anchor point, comes out of the origin going mostly vertical, and then as it passes 1, 1 in the graph, it turns and it becomes more horizontal as it travels off to infinity. Okay, logarithmic function. We did spend a considerable amount of time in the spring looking at the logarithmic function, and its parent function is f of x equals log x. Okay, and then remember this one is the inverse of the exponential function. So instead of crossing positive 1 on the y-axis, it crosses positive 1 on the x-axis. So it comes along quadrant 4, comes up the y-axis in quadrant 4, turns through positive 1 on the x-axis, and as it passes through that location, it stops being mostly vertical and turns more horizontal, and then it heads off to infinity. Okay, the absolute value function, we spent a little bit of time on this one back in the fall. Absolute value function is a function of the form f of x equals the absolute value of x. Now, absolute value functions have a tendency of having a deflection point in them, meaning the graph is heading one direction and then it suddenly and abruptly reverses that direction depending on what's going on with the absolute value. But the parent function looks like this. We have basically a linear equation that is coming, has a downward slope in quadrant 2, and when it hits the origin, that becomes the deflection point, and the graph goes from having a -1 slope to a +1 slope, and that reflects it back up into quadrant 1. Okay, so that was that. The next thing we did is we started looking at the very basics of the transformations that can happen to those parent functions. The first one we looked at was the easiest to deal with. It's the vertical shift. Okay, now realize that a vertical shift is basically just moving the y-intercept in an equation, and you've seen this before, even all the way back into pre-algebra and algebra 1. Okay, slope-intercept form, y equals mx plus b. B was just a constant, and that constant was being added or subtracted to your line, and all that constant did was move your graph up or down, or move your line up or down in the graph. Well, the same thing is true for any equation, any graph that you run into any time. If you add or subtract a number to the very beginning or the very end of the problem, okay, in short, just a constant being added or subtracted, you have caused a vertical shift. Okay, now for the first several months of Algebra 2, we had the vertical shift over on the right side of the problem, okay, away from the isolated variable, and we just read the sign exactly the way it read. So if the vertical shift said +2, then that meant you went 2 in the positive direction, which is up. If the vertical shift said -2, then you went 2 in the negative direction. Okay, so we read it exactly the way it was written, no big deal. Okay, and we showed that that held true for all of the parent functions. All it does is cause upward and downward movement because of those values being added in. Okay, after that, we went into it a little bit deeper and we looked at what we call phase shifts. And while the constant being added or subtracted to the end of the problem caused vertical shifts, moved it up and down, this was the idea that a constant is being added or subtracted specifically to the x value, which of course adjusts the x-axis. So it moves our graph left and right. So it's sometimes called a phase shift, sometimes called a horizontal shift, but phase shift is the appropriate term. Now the trick with these guys was that the sign actually reads backwards of the way that you read it. Okay, and we've seen this plenty of times this year, so that should not be any confusion anymore. So if you see a problem like the one in the middle where you have a 2 being added specifically to the x, well, that was supposed to be a minus sign in between them. The only way that that minus sign could have been taken away is if the 2 had a negative as well. So that means a -2 goes left. Okay, over there on the right, x -2, well, that's supposed to be a minus, which means 2 did nothing to change the sign, so that should be a +2 and shift to the right. Okay, again, we looked at the fact that these all read the same way. They all do the same thing, no matter which parent function you happen to be dealing with, and that was it. The real catch, and the one that people struggled with more than anything, was the idea of the amplitude change. Okay, amplitude is basically just something that increases or decreases the height or the vertical speed of the graph as it does whatever it is that it does. Typically, this value is shown as a coefficient that is directly influencing what is happening with x. Okay, so assuming that we are just dealing with a straightforward, nothing fancy amplitude change, we have a coefficient that is in front of whatever it is that's happening with x. And what we saw is that the bigger the coefficient, the greater the influence as the graph heads towards infinity as far as height, the y value, what it's doing in the range. Okay, so 1 is the parent function. That's kind of the equilibrium point. It's supposed to be a 1 influencing that x, but as the value gets bigger than x, like a 2x, that's going to cause the graph to rise twice as fast as it should have, and values that are smaller than 1 are going to cause the graph to rise slower than it should have. Okay, we also saw that negative values were possible on our amplitude, and when we saw a negative value, that simply turned the graph upside down. Okay, and if you have a negative value that was in there actually influencing the x, then what that caused was the graph to be reversed left to right. Okay, so a coefficient in front of whatever's happening with x influences the range, and a coefficient directly in front of x influences the domain. Okay, so we looked at several examples of that. And that was basically it. Then we had our Unit 2 test, and looking back at that, that probably seems very simple now. Probably wonder how we ever had trouble with that back in the day, but hindsight's always 20/20. Anyway, there's your Unit 1 and Unit 2 combined review, and I'll see you in class.